Okay. All right. Well, thanks for coming to class, and we'll begin. Let's see. All right. So last week, so I get it's already been a week, but the last time we talked about kind of this island hopping example. And we were asking, how do we design a Markov chain? How do we figure out what the transition probabilities should be so that when we let our Markov chain run, the the states that it enters, because it goes to these states stochastically via some kind of random process. And we want to make sure that the states that the Markov chain enters matches some kind of target distribution. So we started off with this discrete case where we said, imagine there's 7 islands, and the islands have these populations, and we want to visit the islands, relative to their populations. And just to kind of make everything simple, we said, you have islands 1 through 7, and the population of island 1 is 1,000. The population of island 7 is 7,000. So we want to visit island 7, 7 times more frequently than island 1. And, island 6 should be visited twice as frequently as, say, island 3 or something like that. And so if you kind of do the math here, this adds up to a total of 28,000, and you would visit island 7 out of 28, or a quarter of the time, and you'd visit island 1 out of 28. So this would be our target distribution, and we want our politician who's kind of going to visit these islands via some kind of random process to end up, visiting these islands with these target proportions. And the algorithm that the politician uses is he flips a coin in the morning, and if the coin lands heads, he's going to propose the island to the west that is, I guess, a number lower, the island that's lower than him. And if the coin lands tails, he'll propose the island to the east. Okay, and even though these are specific numbers and stuff like this can be generalized to basically any kind of discrete distribution with any kind of values, right? And so after he proposes an island, then he checks the population of the proposed island and the population of the current island. And if the proposed island has a larger population than the current island, he will definitely go to the proposed island. And if the proposed island has a smaller population than the current island, then he goes to that island probabilistically. He calculates this kind of probability of moving there, which is the ratio between the proposed populations and the current population. So if the proposed population is, like 99% of the current population, so, if it's, then he's going to end up going to the proposed island 99% of the time. If the island that he proposes has, a population that's half of his current island, then he'll go there with, a probability 1/2 type of thing. Okay, so he can, he will move there with that probability, and to kind of ensure that he moves there with that probability, he generates a random uniform number, and if that random uniform number is less than p move, he'll move to that proposed island. And if he doesn't, then he'll stay at the current island. And this kind of system, it works. In the long run, the probability that the politician is on any one of the island exactly matches the relative population of the island. And we'll kind of look at this a little bit mathematically later. But yeah, it works out. And so we can calculate the transition probability matrix. And so we kind of worked through this in last week's lecture. Lecture 5-2, we found the transition probability matrix, and we said, if we're at say island 4, okay, we'll propose the island to the right with probability 1/2, and we'll propose the island, island 4 is the one in the middle. We'll go to the island to the right with a probability 1/2, because that's if it lands heads, or if it lands tails, we propose the island to the right, and that's going to happen with probability 50%. And then we will propose island 3 with probability 50%, but even after proposing island 3, we will only go there with probability 3 out of 4, because island 3's population is 3,000, island 4's population is 4,000. So we take that ratio, 3/4, and so we have a total of 3/8 probability of going to island 3, and then we have a 1/8 probability of remaining at island 4. And we can go through and calculate these probabilities for every single starting location. If we started off at island 1, we will move to island 2 with probability 1/2, because if the coin lands tails, we'll go to island 2. And if the coin lands heads, then that means we propose island 0, which doesn't exist. So we cannot go to island 0, and we would just remain at island 1 with probability 1/2. Okay, so this is what our transition probability matrix looks like. And I think we also showed that if you take the left eigenvector of the transition probability matrix, the left eigenvector is going to be equal to the target distribution, and that's going to be our stationary distribution. So we have these stationary distributions, which is kind of, so we talked about, Markov chains that are ergodic, which says if you let them run long enough, eventually they will reach kind of their limiting distribution, and if that limiting distribution exists, it will be the stationary distribution, and the stationary distribution is kind of the distribution over the different states, so that once you apply the transition probability matrix, you get back the same result that you started off with. Okay, so if you start off at the stationary distribution, apply the transition probability matrix, you end up back at the stationary distribution. Your relative proportions don't change. So that's kind of where we left off, and so we can actually run the Markov chain. Maybe we did, or maybe we didn't do this. So what you'll see in the code is that we're going to kind of just flip a coin, and we will propose either our current island. So current island is x at time t, and we will propose x at time t plus 1, or x at time t minus 1. Okay, so for island 4, we'll propose island 5 or island 3, and then we'll calculate p move. And so if the proposed island has a higher population than our current island, like if we're proposing island 5, it has a population of 5,000, and our current island has a population of 4,000, we'll get a value greater than 1. So the probability of moving has to be, you can't have a probability greater than 1. So we're going to do the minimum between 1 or, whatever this is. So if P proposed over P current is less than 1, that's going to be your probability of moving. Okay. And then we will decide to move there if our random U is less than or equal to P move. Okay. If it's less than or equal to P move, then we will move to the proposed location. And if U is greater than P move, then we will not move to the proposed location, and the x at time t plus 1, at the next iteration, we will just use our current value. So we will just remain where we are. Okay, so here is the kind of the code here. I have a function that just says propose a value. Okay, and so all it does is it takes your current state, your current island, and it is going to just randomly sample either a 1 or a minus 1, and it will add that to your current value. So that's going to be your proposed thing, right? So proposed is just going to, if you're currently at 4, it's going to either return a 3 or a 5. And then kind of the target probability, okay, the target probability is going to be just whatever x is divided by 28. That's the target distribution. So let's say we use this to figure out what is the kind of probability of our current location, probability of the proposed location. And so if we propose a value, if x is something between 1 through 7, then we'll return that number over 28. And then if it's not, like if we propose an 8 or if we propose a 0, then the probability is going to be 0. So that's this function. So these are probabilities. These are functions that are going to return the probability that we want. So I'm going to just let this run 1,000 times. We are going to start at island 4, and I'm going to repeat 999 NAs. And then I'm going to run this for time t from 1 to 999. So our current value will be x at time t. So I'll start off with 4. And then my proposed location is I plug in 4 into current, and the proposed will either be a 1 or a 5 or a negative 5 or 3. Sorry, 4 plus 1 or minus 1. So our proposed is either going to be a 5 or a 3, and the probability of moving is going to be p proposed divided by p current. Right? So we plug in p of the proposed. So maybe that's 5 over 28. Or maybe it's 3 over 28 divided by our current, which is going to be 4 over 28. And then we're going to generate a random value, a random u. And if u is less than p move, we'll move. Now, technically, p move is the minimum between 1 and p proposed over p current. But I'm not actually going to bother implementing that as a line here, because let's say I proposed island 5, then my p move here is going to be 5 28ths divided by 4 28ths. I'll get basically a 5 over 4. And so my p move is going to be greater than 1. And so when I generate a random u, it's going to be less than p move. No matter what, right? U is going to be less than p move with probability 1. So I don't actually have to figure out minimum of 1 and p proposed p current. I mean, you could do that, but it's not necessary. So if u is less than p move, then the proposed location is going to be what I will use at x at time t plus 1. And otherwise, I will use my current location as the location for x at time t plus 1. Okay. And this is the code to run the Markov chain. All right, is that okay as far as line by line what is happening for running the Markov chain? All right, and while we're here, let me go ahead and give you your first view quiz answer. So this is week 6, Wednesday. First answer is A. A as in apple. A as in apple is our first view quiz answer. Okay, so I will let this run, and this is after 1,000 iterations. So I just kind of create I tally up all of my different values for x. I've got 1,000 of these things, and I say, round this off. So I end up at state 1. 28 times out of 1,000, which gives me empirical result of 0.028. I end up at state 2 68 times, so that's an empirical probability of 0.068. And you can see kind of what we get here. The target probabilities are basically 1 over 28, 2 28ths, 3 28ths, so on and so forth, up to 7 28ths, 0.25 at the end over there. And we can kind of compare these, the counts, the actual counts versus the target probabilities. And so I'll run a chi-squared test between the counts and the actual probabilities, and I get a p-value of 0.6105. And that tells me right now I do not have evidence that that my kind of empirical results are in conflict with the theoretic or, hypothesized results in the null hypothesis. That is my target probabilities. We can kind of plot. The target distribution is shown in gray here, light gray, or I guess white in the projector. And the empirical is shown in the dark bars. And we see there's a fairly close match. We ended up at state 7 a little too much, and we ended up at state 1 a little not quite enough. But overall, kind of in this area, we're getting, fairly close, a little bit of mismatch here. Of course, as the chain runs, it just goes to these locations randomly. So this is kind of the path. One for this, as I ran it, this is just the first 200 values of the Markov chain. We started off at island 4, and it looks like we went to island 5, then island 6. It looks like we stayed at island 6, so we proposed going back to island 5, but didn't go. And then we went up to island 7, went back to 6, 7, stayed at island 7 a few times, went back to 6, back to 7, and then here we went down, 6 to 5 to 4, back to 5 to 4. We can kind of trace out the path. Here it looks like we went down to island 1 and stayed there a few times, and so on and so forth. And so this is kind of just what the first 200 iterations of the Markov chain looks like. And we can see, we end up at island 7 quite a bit, and we ended up at island 1, just very few times in these first 200 values. And the idea is, you just keep letting it run, and we let it run for 1,000 iterations, and we ended up with something that looks like this. And you could let it run even longer, okay? So here I just ran the exact same code, but I just said do it for 100,000 iterations, okay? So after 100,000 iterations, these are the results I got. The empirical probabilities after 100,000, I have 0.0368 versus the target of 0.0357, 0.0740 versus the target of 0.0714, 0.1097, 0.1071, and so on and so forth. And if you look at these numbers, I would say they are pretty close to between the empirical and the target. They align quite closely. One issue, though, and here's the kind of visual representation of that. So again, our target distribution in light gray and our empirical distribution in black here, or dark gray. We see quite a close match between that. However, if you do a chi-squared test, we end up getting a p-value that's very small. And that, I would say, is more of an artifact of the chi-squared test itself. So the chi-squared goodness of fit test is really only effective with moderate sample sizes. So the rule of thumb is you need to have at least a count of 5 for every an expected count of 5 for every category in order to do the chi-square test in the first place. So you need at least a big enough sample. But then at the same time, just the way you calculate the sample, it is, or the statistic is that it just kind of keeps adding the counts. So as your sample size gets bigger and bigger and bigger, your chi-squared statistic also is just going to get bigger and bigger and bigger because it ends up being just the sum of all of these different values. And so with something like 10,000 values, you end up, the statistic just ends up growing very big, and therefore your p-value ends up getting small. So the chi-squared test, generally not recommended for any time you have a sample over, say, 2,000. I would say 2,000. I mean, and that's just kind of a rough estimate of how big your chi-squared test should be. So anyway, I don't know if we have a very good statistical test for a really large sample. There's some discussion as far as like, what do you do for goodness of fit tests? You know, do we have a decent test for very large sample sizes? I think there's some discussion on Stack Exchange about this, but I don't know if we have a great answer. Okay, I mean, you could just randomly downsample, but maybe probably not the best there. Okay, so here we'll just kind of eyeball it and say, yeah, that looks pretty good, and we'll just have to kind of leave it at that, which is, you know, perhaps a little unfortunate, but we have that. Okay, so that is the island hopping example and just letting kind of the Markov chain run here. And, you know, we could imagine this being generalized to any kind of discrete distribution, right? So you just replace all of the different states that you want with some kind of, you know, discrete distribution, and you'll end up getting that, right? Okay, so the Metropolis algorithm is, you know, let's generalize this. So from the island hopping example to just something a little bit more general, and we can just have an arbitrary probability distribution, which we'll just call P of x, and this can be a continuous distribution, not just a discrete one like we used for the island hopping example. And so for now, so today we'll look at the Metropolis algorithm, and then another generalization of it, the Metropolis-Hastings algorithm. And we'll start off with kind of the univariate case, and then and then next week we'll look at kind of generalizing that to a higher dimensional multivariate case. Okay, so what we need is a function that is proportional to the desired target probability distribution. So one nice thing about the Metropolis algorithm is that you actually don't even need to have the exact form of the PDF. So let's say you have this target distribution. You don't actually need to have the exact PDF. You just need something proportional to it. And that's actually very, so let me, that's very handy. So I'm going to skip ahead to this slide, and then I'll come back to this slide. So the f of x, this function f of x, only needs to be proportional to p of x, okay? The exact form of p of x so that it integrates to 1 is not actually needed. You just need something proportional to it. So if we say f of x is equal to c times p of x, you know, where c is some unknown positive constant, then, you know, the probability of moving somewhere is going to be the minimum between 1 and f of x proposed divided by f of x current. And we can see that, well, f of x proposed is just c times the probability of x proposed, and divided by c times the probability of x current. And that's just going to be equal to p of x proposed and p of x current. So when we calculate this p moved, we can just use f of x proposed divided by f of x current without actually having to use the target probability distribution of p of x proposed and p of x current. And why is that a useful fact? Okay, it's especially useful in Bayesian statistics, right? So in Bayesian stats, our posterior distribution, this is usually what we want to get. Probability of our unknown parameters given the data that we have x, okay? So we, you know, in our early example, we had like the beta binomial, and we wanted to figure out, you know, what is that unknown parameter p given the data that we saw. I think we said, like, you know, we saw this many marbles out of the pouch and stuff like that. So this, you know, we want to get this target distribution. And our calculations involved us figuring out the likelihood, which we used kind of like the binomial. We had the prior distribution, which was a beta distribution. And then we had to calculate the marginal distribution in the denominator. And we said the denominator is found by finding the numerator for all possible values of theta, okay, and then summing the numerator across all of these values. Okay. And in our example, we had like for the factories and the marbles, I think. Right? Actually, no. That's like a different thing. But we had like the baseball example and stuff, and we could just kind of sum the numerator across all of the different possible values. Or actually, we didn't bother with it. We just used some binomial beta identities to figure that out. But in another class, we might try to find like all of the different values of theta and sum the numerator across all of the different values of theta. And that could be a very computationally expensive thing. Okay, calculating what this P of X is, the marginal probability, by calculating the numerator across all possible values, either summing or integrating, that could be very computationally expensive. And really, that this P of X is not dependent upon theta itself. It is just it is dependent on the data, and so it is just a constant. Okay, with respect to theta, P of X is just a constant, and so it's just a normalizing constant, so that the entire that this entire thing integrates to 1 or sums to 1. And so rather than trying to find the exact form of P of theta given X, we can just get away with using the numerator only, okay? We don't have to figure out the normalizing constant. And so so next week, we'll do an example where trying to figure out the denominator would be really kind of painful. But we can skip it. We don't have to, okay? And that's gonna make our life easier. So we don't have to figure out the normalizing constant. We're just gonna say, hey, you know what? The target probability is gonna be proportional to our numerator, and so we'll just use the numerator and say that is the function that we're gonna use there, okay? So instead of trying to find that, we'll just use f of theta equal to the numerator. And we know f of theta is proportional to the target distribution. I guess this should be P of theta, and that's what we'll do. Okay, so going back to this Metropolis algorithm, okay, we're going to say we have some kind of function f that is proportional to the desired probability distribution P of X, and we're going to start at some arbitrary location. X at time t, and we'll let that be the kind of first sample in our Markov chain. And then we have a proposal distribution, okay? And the proposal distribution is going to generate a random value using your current value. So you have given your current value, we ask our proposal distribution to generate a random value, okay? And so as far as the Metropolis algorithm goes, this proposal distribution has to be symmetric, but it can be generalized into the Metropolis Hastings algorithm, which does not require it for it to be symmetric. But we're going to say, you know what, if we're at some location B, the probability of proposing A is the same as the probability of proposing location B if we started off at location A. I'll give you examples of this so it makes a little bit of sense here. Okay, and so what we'll do is we will propose a value, x proposed, using our current value, x at time t, using our proposal distribution. So this is kind of like using the coin flip, where we're currently at, say, island 4, and we use the proposal distribution to either propose island 5 or island 3 or something like that. And then we use our function f of x which is proportional to the target distribution to calculate the probability of moving, which is, in our island hopping example, f of x, we could use p of x, which says, island 5 has probability 5/28, and island 4 has probability 4/28 or something like that. But we could have also just used the population of the island, which is proportional to it. We could have said 5,000 divided by 4,000 or something, okay? And that will determine our probability of moving. And then we either go there or we don't, okay? We'll generate a random number u, and if it's less than or equal to p move, we will accept the proposed location, and x at time t plus 1 will be our proposed value. And if our u is greater than p move, we will reject the proposed location, and we'll reuse our current value. All right. So we talked about this. F of x only needs to be proportional, which is very helpful in Bayesian contexts. So what is our proposal distribution? Okay. For the island hopping example, we used a coin flip, and that's a symmetric distribution in that if you are at island 4, the probability of proposing island 5 is 1/2. We flip heads and it lands heads, okay? If you're at island 5, the probability of proposing island 4 is also 1/2. So it's a symmetric distribution, okay? Because the probability of proposing island 5, if you're at island 4, is 1/2, and vice versa. Probability of proposing 4, if you start off at 5, is also 1/2. Okay. For a continuous distribution, okay, we can't use a coin flip anymore. We have to be able to propose values here. And so I would say some common choices that could work would be a normal distribution centered at xt with some arbitrary sigma value. So if you start off at location let's say 4, okay, now you will use a random normal distribution. You'll just use a normal distribution, and you're going to ask R to generate a random value from this normal distribution where the mean is 4. So maybe you will propose, 4.7 or 3.2, or, 95% of your values that'll propose will be between 2 and say 6. 99.7 will be between 1 and 7, plus or minus 3 standard deviations, if your standard deviation is 1. Okay, so you'll just say, your proposed value is going to be R norm, where the mean is your current location x at time t, and you have some arbitrary sigma. Okay, and you can adjust your sigma to be great, large, or small, depending on what it is. You can also have a uniform distribution centered at x at time t with some arbitrary width, maybe 2 times some constant. So you'll go up or down some constant value. And so you could say, I'm going to propose one random uniform value between x at time t minus c and x at time t plus c. So these are just 2 simple examples for what a proposal distribution could look like. And it's a continuous thing so that you can generate any kind of value, in some kind of given range here. Okay. You could have other distributions as well. Instead of a normal, you could use a t distribution or whatever if you wanted to have heavier tails or something like that. Okay, so this is a silly example, but let's say the target distribution that we want to generate values from is going to be a normal distribution centered at 15 with a standard deviation of 3. So the PDF is going to be 1 over sigma root 2 pi e to the negative 1/2 x minus mu over sigma quantity squared. And if I plug in our desired values of mu being 15 and sigma being 3, this is what I would get. Technically, I have this normalizing constant, 1 over sigma root 2 pi, but just to kind of illustrate that we don't actually need the normalizing constant. We just need something proportional to the target distribution. I'm going to just drop it. Okay, and so here I have a function that is not exactly the PDF, but is proportional to it, and it's just e to the negative 1/2 of x minus 15 over 3 quantity squared. And then for a proposal distribution, I will use a uniform distribution centered at x at time t with a width of 6. So we'll go plus or minus 3. Okay? And then, and just to kind of illustrate how this algorithm works and how effective it is, I'm going to start with the really terrible starting location of x, our initial value being 100. Okay, so again, you know, the target distribution is centered at is a normal distribution centered at 15, which means 68% are going to be between 12 and 18. 95% of our values are going to be between 9 and 21, 2 standard deviations, and 3 standard deviations would be 9. And so 99.7% of our values are going to be between 6 and 24. Okay, so the idea of this distribution generating a value at 100 is kind of absurd. It would never do that. But I'm going to go ahead and just start my Markov chain at 100 because what I want to show you is that with this algorithm, wherever you start, even if it's at a terrible starting location, if you let the Markov chain run long enough, it will eventually find its way to where it's supposed to be and then generate random values from kind of the target distribution. So, so this is what our code would look like for generating, using the Metropolis algorithm. And so I hope we can read this. So this function f, this is going to take whatever, this is the function we use to get, you know, f of the proposed location versus f of our current location. And again, this is just proportional to the target PDF. It's e to the negative 1/2 times x minus 15 over 3 quantity squared. And so it's not the PDF, it's just proportional to it. And what we're going to do is we're going to plug in our current location. We'll plug in our proposed location to kind of calculate that value. I have a proposal function. The proposal function just takes in our current location, and it's going to return a random value, one random uniform value sampled between current minus 3 and current plus 3. So wherever I'm located, I'm going to just propose a location. Okay, we'll let this run for 5,000 iterations, I guess 4,999 iterations, and I'm going to start at the terrible location of 100. And how does this go? Okay, we will take our current location, x at time t, so starting off at location 1, or time 1, I'm going to plug in 100, my current value is 100, and I'm going to propose a value, right? So I'm going to propose a value, random value between 97 and 103. So let's say I propose 102, okay? I'm going to calculate my p move. I'm going to say, all right, what is, if I plug in 102 into my function, I'm going to get back some kind of number. And if I plug in my current value of 100, I'm going to get back some kind of number, right? So plugging in 102, basically this, okay, plugging in 102 here, we can see this e to the negative whatever is going to get bigger, so that's going to get smaller. So the probability of moving towards 102 is lower, right? Because I'm doing 102 minus 15 over 3 quantity squared versus 100 minus 15 over 3 quantity squared. We're going to get, and these are e to the negative that. So these are very small probabilities, but I'm going to get some kind of value for p move, and then I will generate a random uniform value, and I'm going to say if u is less than p move, we'll go to that proposed location of 102, and otherwise we're going to stay at 100. Probably we will end up staying at 100, okay? Let's say at the next iteration, I propose, say, a location 95, okay? if I propose, or not 95, 98, okay? So if I propose 98, then I get 98 minus 15 over 3, something squared, and that's a smaller number, and then versus 100 minus 15 over 3 quantity squared. So we're going to get f of x of 98 is a greater number than f of 100. And so we will, our p move is going to be greater than 1. And so we would accept that in that case. Okay, and we just kind of let it run. And so in the beginning, I'm starting off at 100, and I will probably just start drifting towards kind of where our values should be. We can see that if I start off at 100, as long as x is greater than 15, okay, whenever I propose a number that's closer to 15, this f of x is going to get larger, right? Because here I've got x minus 15 quantity squared. And then eventually I might get to x at 15, okay? X is 15. And then so now, when I propose values going away from it, we're going to get values that are a little bit smaller. And so, but we still have a probability of moving in that direction because if the proposed location has a lower probability than my current location, I can still go there. It's just I take the ratio between f of the proposed location and f of the current location. So anyway, I run the chain, and this is what our chain kind of looks like. I start off at 100, and in the beginning, it just moves towards kind of our target location of around 15. If I zoom in here, we can see, there's there's a few locations where, so here I start off at 100 and I probably proposed 98 or whatever, and I end up moving there. And then there's, a small period here where I probably, just by the random proposals, I proposed values in the opposite direction, and they didn't accept those, okay? So I didn't accept things that were getting proposed. So we, end up with these small kind of flattish regions. But overall, we just kind of keep drifting closer and closer until we get to kind of our target location. And and then we start generating values around here. So despite starting at this kind of terrible location of 100, we end up finding kind of where we're supposed to be in around 180 iterations or so. And so this initial part where I have these terrible values, we call this the burn-in period of the Markov chain. So a lot of times when you do run a Markov chain, it's because you don't know how to generate values directly, and you don't know what values you should even start off with. So you just start off with some arbitrary location, allowing kind of this Metropolis or Metropolis-Hastings algorithm to kind of run its course. And then and at the end, you kind of look at the distribution, the values that have been generated, and you say, all right, let's go ahead and just throw away these first 100, first 1,000, maybe even more values away, because that's just part of the burn-in period of the algorithm running until it kind of finds where it's supposed to be. So here I went ahead and I discarded the first 180 values, again, the burn-in period. And with the Metropolis algorithm, again, we can give it some poor starting locations, just allow it to run for a while, and then eventually it finds the place where the samples should be abundant. So here I said x keep is, we're going to just throw away the first 180 values of x. Let's make a histogram of x keep, and this is what it looks like. And yeah, it looks like, in red I have the theoretic distribution of a normal distribution centered at 15 with standard deviation 3. And it looks like our values kind of match, okay? Here is the plot between the theoretic CDF in red versus the empirical CDF. And it looks like we have a pretty decent match. And that's what it looks like. Okay. Now, one shortcoming of the Markov chain is that the values generated in your Markov chain are not going to be IID. Okay, they are not independent. The next value generated by your Markov chain, by definition, depends on your current value. Okay, and so this is what IID values look like. So here, if I just say, hey, give me 1,000 random normal values, this is kind of what IID values look like. It just kind of bounces all over the place. Centered at 15, standard deviation 3. This is what IID values look like. This is what our distribution looks like. Okay, and so rather than just kind of having totally random values, we can see, oh yeah, it's a little bit more like a random walk, right? We can kind of trace out a path where a guy moves to the right or moves to the left or something like that. Okay, I mean, certainly back here we see more of the random walk nature of the random walk here, and this is kind of like even after I throw away the burn-in period, we can see there's still a bit of this random walk thing. So there's a few kind of ways to deal with this, and one is, so there's a thing you look at, autocorrelation, which is kind of like how much does my current value, how correlated is it with the previous value? Okay, so you kind of ask, like, if I take all of my values and I just shift it down like one block, what's the correlation between this and kind of like the one previous value? And if there's high correlation, you might say, okay, well, let's filter it to just every other value. Okay, so you end up throwing away some of your values. And if you still have high autocorrelation, then you can try saying, let's shift it down 2 or 3, and you can do like kind of this autocorrelation with a lag of 1, lag of 2, lag of 3, so on and so forth, where you're going to say, okay, if I take every single value, there's going to be kind of high dependence between our current value and the previous value. So I can try, just filtering this to like every other value or every third value or every fourth value until you get values that look like they are IID, if that's important, if it's important for you to have IID values, or at least something that resembles IID values. Okay, so this is kind of what our chain looks like, and again, we can kind of filter some things out. Let me give you your second view quiz answer, which is the letter C. C as in cat. C as in cat. Our proposal distribution was an arbitrary choice. I think it's a decent choice, but it was arbitrary. I just said, hey, I'm going to propose values from the uniform distribution with a width of 6. Now, I could have also used other proposal distributions, and just to kind of illustrate the effect that we get, I'm going to just do some wild extremes here. And so one is I'm going to propose values, random uniform values, centered at x at time t, but with a width of 100. So if I start at, say, 50, I'm going to propose values anywhere from -50 to 150. Okay. I can also propose values with a width of 1. So if I'm at 50, I'm going to propose values between 49 and 51. And then we can try a width of 12. Okay. So actually, I'm going to start my chains at 15, so I don't have to worry about a burn-in location. We're already going to kind of be at the where we want values to be proposed from. Okay. So I use the exact same code. The only thing is I'm going to, a width of 100. So I'm going to take my current value minus 50 to current value plus 50. And this is what my Markov chain ends up looking like. Let me just kind of zoom in here. So, I started off at 15, and, we end up getting this, it almost looks like a city skyline, in that there's like these flat things, and we get these things that look kind of like buildings and stuff. And basically what happens when I get these flat regions is my Markov chain is proposing values that I'm rejecting. And whenever I reject a value, I reuse my current value. So here I'm at like 15.5 or something. And basically the Markov chain is proposing values between 15 plus 50 and 15 minus 50, or 15.5, so we're proposing values, say, between, I can't do the math, 34.5 and 65.5, okay? We're proposing values between 34.5 and 65.5, or negative 34.5. And so if I propose a value like negative 30, and we say, all right, what's the probability of looking at our target distribution? Well, the target distribution is never going to generate a value of negative 35 or negative 34 or whatever it is. So it's going to, the probability of going there is going to be 0. So we reject it. Okay. If I propose a value like 60, what is our target distribution will never generate a value from 60, or not never, but incredibly low probability of going there. So the probability of accepting 60 is pretty much 0. So we end up just rejecting a whole lot of values, and we just keep reusing the same value over and over and over. And so I get kind of this flat region. Finally, I generate a value like 13.5, and we accept it. Okay. Here I generate a value like 17 or 16, and I accept it. I generate a value 21, and I accept it. But there's also places where, I get kind of stuck, where all of the values I'm generating, or the Markov chain is generating, just kind of gets rejected. Okay, so with a very wide proposal distribution, a lot of these proposed values fall in these regions with very low probabilities. They all kind of all of these proposed values get rejected, and we just recycle the same value. Okay. Here we're going to propose values with a width of 1. So I'm going to take my current value. I'm either going to go plus 0.5 or down 0.5. Okay. And this is what our Markov chain ends up looking like here. Okay. So what ends up happening is that my proposed locations all end up being very close to my current location. So if I start at 15, then I'm going to propose a value like 14.5. I mean, that's the most extreme value I can generate, or I'm going to generate a value like 15.5. And so basically, my x proposed value is very, very similar to my x current value, which means my f of x proposed is very, very similar to my f of my current value, right? And that means my probability of moving is going to be close to 1 for almost all of these things, okay? And so pretty much if I start off at 15 and I say, hey, I propose 14.8, should I accept it? Okay, the f of 14.8 and the f of 15 are very similar to each other. And so even if 14.8 is less likely than 15, I might have like a 90% probability of accepting it. Okay, so most of the time I accept all of these proposed values. And so my Markov chain looks like this, random walk with very tiny steps, because I keep proposing these locations that are really close by, and we just kind of move in tiny little increments, and eventually the chain will kind of drift into all of its regions. One thing about these Metropolis algorithm Markov chains is, theoretically, if you let them run long enough, you will get the appropriate distribution. It's just you might have to let it run for a really, really long time. But theoretically, it should do it. But this is your proposal distribution, is proposing values that are too close to the original value. Almost every value gets accepted, and it looks like this. Okay. So here's something maybe in between, taking our current value, going plus or minus 6, and this is what our Markov chain looks like. And again, remember, our dream ideal case is something that looks IID, which is this. And we're not quite IID, but I'd say this as far as the different chains that we've produced, this is the one that looks the closest. And if we, then filter this further to just like every other value, it'll probably look pretty good as far as, say, something that looks like IID values. Okay, let me talk about the Metropolis-Hastings algorithm, which is a further generalization of the Metropolis algorithm, where we relax one of the restrictions on the generating distribution. And so, sorry, for these notes, I just kind of I have them handwritten here, okay? So with the Metropolis algorithm, the proposal distribution, we said the proposed location, which I wrote as x prime, okay? The proposal distribution has to be symmetric, that g of x prime given g at x at time t is the same as the probability of proposing x at time t if we're currently located at x prime. So I said, probability of proposing x prime if we are at state xt is equal to the probability of proposing xt if we are at state x prime. So here, this is the idea of us being centered at xt, and I'm proposing x prime if I'm using a normal distribution. And over here, if I'm centered at x prime, because it's symmetric, the probability of proposing xt, these two things are equal, okay? These two probabilities are equal because g of x is symmetric. The Metropolis-Hastings algorithm does not require that the proposal distribution be symmetric. It is possible for these two things to be unequal. And, I would say in a lot of cases we end up using a symmetric one, like the normal distribution, but Metropolis-Hastings just doesn't require that restriction. It would be kind of like if we go back to the island hopping example, instead of flipping a coin, I guess you could have like some kind of biased coin that lands heads more frequently than it lands tails. So you end up proposing like islands to the left more often than you propose islands to the right. And even if that were the case, as long as you take that into account, the fact that your coin is biased to land heads more often than tails, as long as you take that into account, you can still get it to work. That's basically the Metropolis-Hastings algorithm. It's just saying like, okay, just take into account that the fact that your proposal distribution is not symmetric. As long as you take that into account in your calculations as far as your p moving, then it'll work, okay? So the Metropolis-Hastings algorithm is basically the exact same thing as the Metropolis algorithm. It's just when you do your p move, you take into account the difference in the proposal probabilities, okay? So you start off at a initial state x0, and you have some target distribution p of x, and again, we only need a function that is proportional to p of x, some function f of x. We're going to propose a candidate location x prime, or in the other notes I have it called x proposed, and we propose a location x prime based on our proposal distribution g of x, which is no longer required to be symmetric. And then we calculate our acceptance ratio, the probability of moving there. Okay, probability of moving there is the minimum between 1 and p of x proposed, or x prime, divided by p of xt, or f of x prime, and versus f of x at current, whatever it is. So this part's the same, and then all we have to do is we just multiply it by taking into account the fact that g of x is not symmetric. So when g of x is symmetric and you have the Metropolis algorithm, this part is just equal to 1. The probability of proposing x at time t, given that we are currently at x prime, and the probability of proposing x prime if we're currently at xt. And the Metropolis algorithm, those two are equal, and so this just is 1, and you got basically what we have in the Metropolis algorithm slides, which is this, okay, f of x proposed divided by f of x at time t, or f of x prime divided by f of x t. But Metropolis Hastings algorithm just says, okay, if those things aren't equal, then just take into account the fact that they're not equal, okay? And then either accept or reject your proposed location by generating a random uniform value. And then if it's less than p move, accept it. And if it's greater than p move, then reject it and reuse your current location, okay? So that's the Metropolis Hastings algorithm. It just says, hey, take into account that your coin is unfair. And if you do that, then it works, okay? And so I said, I wanted to, 10 minutes, okay. I wanted to kind of just demonstrate mathematically that this algorithm kind of works, right? And so we'll show that it works for the Metropolis Hastings case, and if it works for the Metropolis Hastings case, then it will work for the Metropolis algorithm, which is just a, I guess a special case of Metropolis Hastings where g of x is symmetric. And so what we want to show is that this Metropolis Hastings algorithm, it works because there's something that we call detailed balance. And we had this little illustration on one of the websites where we had like the balls kind of flowing from like California to New York and New York to California. And the idea of detailed balance is that the amount flowing from one state to the other state is equal to the amount flowing from that state to, like you pick any two states in the chain and you look at like how much is flowing from one to the other and flowing from that one back, is that they are equal to each other. And this is going to be true for basically any two states, even on a continuous distribution. If you pick like x of t is 1.1, or one location being 1.1 and another location being like 1.23, and you kind of figure out like what is the amount flowing from one to the other, you have detailed balance, okay? The amount flowing from xt to x prime, whatever locations you have, is exactly equal to the amount flowing from x prime to xt. And this is true for any two states, okay? If all the states follow this target distribution of p of x, okay? So p of x is the probability of being in state x in the target distribution. And then we have p of x prime given xt, that's going to be the probability of transitioning from state xt to state x prime. And what we want to show is that the probability of starting off at state xt, that is p of xt, times the probability of transitioning to x prime from state xt, that this is exactly equal to kind of the amount flowing in the other direction. That would be the probability of starting at state x prime and then the probability of transitioning from x prime to xt. So we want to show that the amount flowing from this state to this state, this arrow, is exactly equal to the amount flowing in the opposite direction from x prime to xt. Okay? And the trivial case is if the proposed location is rejected. If the proposed location is rejected, right? So sometimes we propose a location and gets rejected, then the next state is, x prime is equal to xt, that basically the next state. And so both sides of the equation are equal. So we don't have to even prove that one, because if we reject it, then the next state is our current state. So the amount flowing to itself is the amount flowing to itself. Okay, but this is kind of the math that we will work out. So what we want to show is that this side, that is the amount flowing from xt to x prime, is the amount flowing from x prime to xt. So here we're going to replace what is the probability of flowing from x prime to xt? Well, that is equal to the probability of proposing x prime given that we currently are at xt, okay? So this is the probability of proposing x prime, and then times the probability of accepting it, okay? And the probability, that is the P move, the probability of accepting that is the minimum between 1 and, this is the acceptance ratio for the Metropolis-Hastings algorithm that we look at, probability of the proposed location divided by probability of our current location times kind of this, we take into account the, proposal probability of getting xt given x prime and divided by proposal probability of proposing x prime given xt. And so what I'm going to do is I'm going to take this quantity, g of x prime given xt, the probability of proposing x prime given xt, I'm going to distribute it through this minimum function, okay? And then this 1 I'm going to replace with probability of xt divided by probability of xt. So as long as probability of xt is not 0, I'm allowed to do this, okay? And we're going to just assume that we're not entering like some zero probability location. And so what I have here is I've got probability of xt times the minimum of, so I replaced 1 with probability of xt divided by probability of xt, and I've distributed g of x prime given xt into here, and then I've distributed it into the other side of the comma, right? And g of x prime given xt, these cancel each other out, okay? So now I have p of xt times the minimum of this, and I'm going to go ahead and distribute the p of xt through kind of both sides of this minimum function. So when I do that, now I have p of xt times p of xt divided by p of xt times g of x prime given xt, and that p of xt cancels out with this one. So I'm left with probability of xt multiplied by g of x prime given xt. And then when I distribute this to this side over here, I'm going to get probability of xt. That cancels out with this probability of xt, so I'm left with probability of x prime times g of xt given x prime. So on the left-hand side, the amount kind of flowing from xt to x prime is going to be equal to the minimum between the probability of starting off at xt and kind of the probability multiplied by the probability of going to x prime given xt, and the minimum of probability of x prime times the probability of proposing xt given x prime. So this kind of, we have the minimum between these two things. So that's going to be the amount flowing from one side to the other. And then using the same logic on the right-hand side, so I won't talk through all of this, but you can kind of follow all of the math. Basically, it works out to be exactly the same thing. Now I have x prime's probability of x prime over here, and we're going to kind of distribute it all of these through these things. All of these things kind of cancel each other out, and we end up getting the exact same thing here. That the amount flowing from x prime to xt, okay, is going to be the minimum between probability of x prime times the probability of proposing xt times the probability of being at xt times the probability of proposing g of x prime, okay? And then in the Metropolis case, so this is from Metropolis-Hastings, in the Metropolis case, these things, g of x prime divided by g of xt and all of that, it's symmetric, so they all kind of just, they just end up being equal to each other. So, you end up getting the same kind of thing as well. So anyway, if you kind of work through the math of trying to show that we have detailed balance, that the amount flowing, you pick any two states, the amount flowing from x at time t to x prime, or the amount flowing from x prime back to xt, for any pair of states, you're going to find that that the amount flowing is equal, that that these two things are exactly equal to each other. And so that's why the Metropolis algorithm and the Metropolis-Hastings algorithm works, despite kind of the procedure being almost deceptively simple. We just say, hey, let's propose a location and let's decide to kind of go there or not. And if you use that as kind of the rule for what your transition probabilities are, then your Markov chain, when you let it run long enough, will end up producing values from that desired target probability distribution. Okay, that's it for today's lecture. Last view quiz answer for today is the letter E. E as in elephant. E is your final view quiz answer. And we will wrap it up here. Have a great weekend, and we will see you next Monday.